Hello, everyone. I'd like to take the opportunity to introduce our next speaker. So if we could have everyone sit back down for the next talk. Next, we have Dr. Jun Yi, and he is a fellow of GILA and a fellow of NIST. His research focuses on the frontiers of light matter interactions that include precision measurement, quantum science, ultra cold matter, and frequency metrology. And today he's going to talk about quantum sensing and fundamental physics. So I'd like to welcome Jun.
Thank you. Well, good morning. I was fortunate to be joining the previous session at Carleton, and I see a lot of active exchange. And I would welcome that. If you do the same thing during my talk, if you would like to raise your hand and have questions, I would rather having interactions with you than finishing my talk. So I don't have to finish my talk. I think I welcome any interruptions as well. So I'm going to tell you, I actually adjusted my talk as I was listening to Carleton's. Remember, he was challenging you, find an application for quantum computing or analog quantum computing. And I just want to put this right up front. I'm an atomic physicist. I build atomic clocks. And I will actually tell you something about really interesting new development of a nuclear clock that's coming out of the Oak Ridge National Lab. But the reason why I'm using this as example is telling you something really truly exciting, the quantum frontier that's making a huge advance today. Okay, we're not talking about 10 years down the road, 20 years down the road, some fluffy things. We're talking about something very concrete, and it's going to have a major discovery impact for our understanding of the fundamental nature of science and the physical world around us, the cosmologies, the universe, and so on. And I'm saying this because I'm giving you some examples. We can cool atoms down to very low temperatures. We can confine them in a lattice made by laser beams. And here shows a cartoon kind of a picture where I can have 1 million atoms confined in an artificial crystal that's made by us, okay? The atoms are in the form of gas, but we can do laser cooling and putting them down into exceedingly low entropy quantum systems. And if I can have a quantum coherence of several minutes, which we have demonstrated in the lab now, with 1 million atoms, you will be able to build a clock with 1 second averaging time reaching a measurement precision of 10 to minus 20s. 10 to minus 20 is the scale when people first heard gravitational waves 6 years ago. That's about 10 to minus 21 when the gravitational wave comes, the space-time start to ripple. And at 10 to minus 21 sensitivity, you will see the space changes due to gravitational wave. Well, of course, time is related to space, and you will expect a similar sort of sensitivity we'll see. So that means you can build an atomic clock, you will start to sense some very fundamental physics. However, when you pack so many atoms together, it's going to impact the light atom interactions. And this is going to limit the fundamental measurement precision if you do not understand the problem. So here's Carleton's challenge of please find an application that will require you to have an analog quantum computer. Here's an example right there. If you do not understand the Fermi-Hubbard model, this 3-dimensional crystal where the atoms are interacting with each other and then interacting with the light field, you wouldn't be able to trust the measurement you're making. And so in some sense, quantum simulation and quantum sensing are very much the same story. Okay, here's a complex Hamiltonian. If you make some approximations, that goes into the 3-dimensional Ising model, exactly what he was talking about earlier. And in order to solve this problem, you put actually native fermions in there, and you can actually drive a lot of interesting physics. And remember, during his talk, one of the students was asking the question, well, you know, this doesn't look like a computer, it looks like a physics experiment. And it's almost like apologetic. Carleton was, oh yeah, you know, it's hard to distinguish whether it's a physics experiment or a computer. I'm not going to come here and apologize to you. I'm doing physics experiments. And I will say the first thing I would say, emphasize the quantum computer. What is quantum computer going to benefit? It's going to be physicists first. It's always true. We are the ones who are building these hardwares. You're going to do the physics experiments first. So this is where the angle I'm coming from. It's a super exciting time because it's a quantum system where you can put the particles one by one and manipulate them. The technology-wise, you're going to build incredible sensors. Scientific-wise, you're going to open new capabilities that had never existed before. And this is in the next 50 minutes. I hope that's the excitement I want to share with you. Okay. And so that's the opening statement, the connecting to the previous lecture of Carlton's. But now I'm going to tell you a little bit about why quantum sensing is, in some sense, quantum science is a continuous spectrum. Whether you're doing information processing or you're doing sensing or you're doing communications and so on, they are all together. The idea being able to have as many quantum particles you can have and maintain quantum coherence, put entanglement in there. And you can use this to do many different things. Fundamental physics is the one area I'm going to focus on. But of course, many of you coming from nanoscience, material science, in the future, some of you may find quantum applications in biology systems, in chemistry, for secure networking of communications and so on, and for information processing, quantum computing. So they are all interconnected. And I do not want to make, oh, I'm doing quantum sensing, or you're doing quantum simulation. I want to emphasize they are the same goal. In the case of when we were talking about this particular picture, when I was telling you about, I was talking with Misha Lukin. Misha's experiment was discussed in Carlton's experiment. We were talking about exactly the connection between optical lattice and optical tweezers, how this joint work of quantum simulation, understanding the complex material science, will have a major impact on the fundamental measurement science. Okay. So with that in mind, you may have seen similar pictures like this from John Preskill's talk at the very beginning. You look at the fundamental physics, you will say, over the past 400 years of science, we have built two scopes, basically. You build a telescope and you build a microscope. That's we had to understand. We build a telescope because we want to understand the whole universe. We build a microscope because we want to understand microscopic pictures. And if you think about all the physics knowledge or chemistry knowledge you have learned, you can't really escape these two scopes. It always comes down to those. And I think what's really exciting now is that we can start to put quantum complexity into the building of those scopes. The scopes used to be built based on single particle physics. You collect individual photons, or you manipulate individual atoms and so on. But suddenly now we can put entanglement in there. There's a quantum complexity, there's a connection to quantum physics, to many-body physics, and so on. But I argue this also represents the frontiers of measurement science. And by advancing the frontiers of measurement science, it comes back to allow you to probe the basic fabric of space and time in the universe, and allow you to understand even high energy, particle physics coming from a quantum computer. And you say, what is the quantum computer's application? How can you find an even bigger application than understanding the universe? So that's the quantum science right here. I think it's happening right now, and we need to take advantage of it. And I also want to make one more point. There was discussing about quantum advantage, quantum supremacy, and so on. And let me tell you this. There's no quantum supremacy. Nobody has demonstrated except the one single experiment, which is LIGO. LIGO, people were able to use squeezed state of light and actually showed if you just use more photons, it didn't help because you have a quantum back action. No other experiments have shown quantum advantage. Let me just put it that way. But on the other hand, every day we're doing quantum science. We, of course, are showing quantum advantage. I wouldn't be able to put 1 million atoms together to show you 2 minutes of a coherence time if I don't deal with quantum science. But we also want to be fact-based, and we're making sure that the real advantage is something that you can never achieve if you do not use entanglement. And that's just simply not true yet. Entanglement is giving you a lot of interesting complexity physics and so on. There is analog quantum computer, as Carlton talked about, where you can have solving some complex Hamiltonians now that will take classical computer much longer to be able to solve. But is there a proof saying, no, classical algorithm will never be able to solve this problem? Not yet. right? That's why fault tolerance in quantum computing, truly digital quantum computer to do universal quantum computing, such a device does not exist. When people make those claims, be very suspicious about because there's no mathematical proof until you say, I can do fault tolerance. Yes, please. Yeah. Yeah, this is a really important question. It's, in fact, that question alone is at the core of the so-called quantum revolution of quantum computing. It's the same thing.
Can you repeat the question for the recording?
Yeah, the question is that these quantum particles are extremely fragile. They can be easily disturbed by environment. How can you use them to sense something very feeble? Is that basically the rephrasing your question, right? Yeah, and I was trying to say, yeah, this is the question at the core of the challenge of quantum science. How do we put millions of quantum particles together? They all enjoy the same quantum coherence. So you can ask them to interact as you wish, but you do not want environment to come in to degrade these quantum qubits qualities. And that is the core. That's exactly what we are trying to do. It's easy to control a single particle. Getting 2, 3, 4 all lined up and having them interact gets harder and harder. And so whether you're building quantum sensors or whether you're building quantum computer, quantum communication, if entanglement is your resource, it's just very, very easy to be perturbed. And that's your goal, is to protect the quantum science where the scale of quantum systems getting bigger, both in terms of temporal as well as spatial dimensions. And how do we make sure it's a quantum system, keep it to be a quantum system? And that's at the core of the quantum revolution right now. It's not easy, but I will see some examples of that in my talk, I hope. And I'll tell you exactly the technology we're doing to make that happen. So to give you some examples of quantum sensing, this is not my experiment, but people actually, for example, back in the 1990s, people start to split quantum mechanical particle wave packets, like atom wave packets, by using photons. You can put atoms in coherent superposition between ground state and excited state. And because of the photon momentum, ground state, excited state can take different trajectories in space, and you can then bring them back into sphere, almost as if a double slit experiment. You have a photon hitting double slits, you can be split out and then recombine. And during this process, when you recombine, there's action differential action taking place between the two different trajectories, and you can use that to sense, for example, gravity. And the modern technology now has taken the coherent superposition to be over 50 centimeters of distance. You can imagine the quantum mechanical wave function, which is actually coherent over that 50 centimeter length scale. And that's obviously very difficult, going back to that question of how do you make sure they do not become decohered because there's all the environmental noise out there. And that's what we do, try to make sure that the noisy environment is well controlled such that the quantum coherence can stay. And you can bring this back into sphere. The larger the separation of these quantum coherent wave functions, the more sensitivity you will have against measuring, for example, gravity. Another quantum sensor, that's probably a little bit more familiar to everyone, is just looking at the two-level resonance. This is the technology you have heard of magnetometers to measure magnetic field. Suppose you have a spin half, spin down, spin up, and this energy scale is proportional to magnetic field B. So by just measuring the energy spacing as a function of magnetic field, you can use this as a very good quantum sensor for magnetic field. And the current technologies is by using more particles to give you the sensitivity, enhance the sensitivity, or using entanglement even to continue to try to increase the quantum advantage. And as I mentioned earlier, no quantum system right now using entanglement has exceeded the quantum magnetometers without using entanglement. But the game is playing. Even in the clocks, we are starting to implement entanglement and so on. The reason why I want to give you these two examples is I want to show you one experiment that it will take you to appreciate why the quantum technology is having such impact on fundamental physics. So here is a measurement of a very fundamental constant called the fine structure constant alpha. Well, that's the basic constant governs how electrons interact with photons, fine structure constant alpha. You can use this technique of atom interferometer that I briefly talked about. And if you can measure, for example, the photon momentum, h bar k, over the mass, this is like every time an atom absorbs a photon, there's a recoil kick. If you can measure that recoil kick momentum against its mass, turns out through some algebraic manipulations of mass ratios and Rydberg constants, you can determine the fundamental fine structure constant alpha to 10 digits. Okay, so the interferometer is not just used for measure gravity. You can actually use this to measure some fundamental constants in physics. On the other hand, people like Jerry Gabriels can build single electron trapped, ion trap of single electrons, and he can measure quantum jumps of those single electrons. The electron has both spin down and spin up, exactly the magnetometer physics I was telling you in the previous slide. At the same time, its motional states are quantized in these ion traps, and he can measure every single of these quantum jumps. And by doing that, he can very precisely measure also this, so through the so-called G-2, you have all heard about electrons has a gyromagnetic moment, and it's not exactly 2. It's in the fact it's different from 2 is because of the electron has electrical field surrounding it, and you have to do renormalization. And this is what Feynman's diagram is all about, making so-called radiative corrections of electron bare mass. And this has consequences where the so-called magnetic factor, the gyromagnetic factor G is not 2. And by measuring G-2, you're testing the QED theory to the highest level of precision. And again, he could do that to the level of 10 digits. And you can see these interesting measurements. One come from very, very different technology. One building atom interferometers. The other one by measuring the magnetic moments of electron. And yet they can come together and compare against each other at 10 digits. And this is not theory calculations. These are real experimental measurements of fundamental quantities at that level of precision. You have to marvel the success of quantum physics, right? 10 digits of theory ab initio calculations that will show this kind of agreement on the experimental side. And this is oftentimes people celebrate this as a great success of the so-called standard model of particle physics. Yeah, yes, please. Yes, this is the 5th order. And you need to, in fact, as experimental precision keeps going, you're going to challenge that. It is challenging, this is raised to the power alpha to the 5. But meanwhile, while the standard model has been tremendously successful, we also know that it's not complete. We know that for a fact. And that's because we have made astrophysical observations, the existence of dark matter. And we have no idea what dark matter is. That's why it's called dark matter and dark energy and so on. And so wouldn't you want to be a person who builds a quantum computer and understand the origin of dark matter? These are the things which are elusive and beyond the technology. Maybe we will never be able to find out what dark matter is until you get very close to black hole. Well, but maybe we can start to make images of black hole now using gigantic telescopes that we can use quantum technology to build the network of these telescopes. And these are the ideas can inspire you from doing these quantum technology, quantum information, quantum sensing to have these fundamental understanding of what's going on, the mysteries in the universe. One of that mystery of the universe is the matter-antimatter asymmetry, in addition to dark matter and dark energy and things like that. The very fact that we exist here, we do not have our antimatter of ourselves existing in a different universe. At least we do not see them. And there's something that's been violating that symmetry, because at the Big Bang, everything should be equal. There should be equal amount of dark matter, antimatter and matter, and they should be annihilating each other, but yet we exist today. The reason is because there's amounts of symmetry violating physics in existence. We all know there's a CPT, parity, time reversal, and charge conjugation symmetries out there. But we also know that for exotic physics to exist, and we already know CP violation is violated, CP violation exists, which means that time reversal symmetry is actually broken, and we need actually more amount of a time reversal symmetry to be broken to be able to really understand where the dark matter is coming from, or maybe where the antimatter-matter symmetry is anti-symmetry is coming from. So advanced quantum sensing can have a major breakthroughs, and I'll give you one example again. I just mentioned that electrons have magnetic moment, and you apply magnetic field, electrons lined up. Carlton even gave you an example of the little electrons moving around the external magnetic field. And I mentioned earlier, you needed to have a radiative correction, and that's the expansion of the, basically the Taylor expansion of it raised to the power of alpha, the fine structure constant. And that's all triumph of QED physics, that Feynmans and Dysons and so on that laid it out back in the 50s and 60s. On the other hand, imagine the electron also has electrical dipole moment. You will immediately see that's going to be very weird, because if you reverse the time, the current will reverse, but electrical dipole moment wouldn't. And so if the electron has both magnetic dipole and electrical dipole, it will violate time reversal symmetry. And you will say that's not possible. In fact, it is actually possible. The standard model take that into account at a 10 to the minus 40 electron coulomb centimeter. It is violated, and so that's built in the fundamental sort of a particle physics of standard model. But what we need is to have this violation to be much, much greater in magnitude to be able to explain the antimatter asymmetry and so on. So you probably have heard in standard models, people have invented theory, and as I want to say invented because the standard model is not complete. People are trying to invent sort of different kind of extensions of a theories for standard model. They say every particle has a supersymmetrical particle that as their partner. Electron will have a supersymmetric electrons as a partner. And if that's the case, there's some high energy particles, much heavier mass, associated with every single particles that we talked about in existence in the standard model. The consequence of that is that just like a radiative corrections, if you have a supersymmetrical particles, you can actually lead to the bigger violations of a time reversal symmetry. Okay. And so this is by looking for time reversal symmetry or CP violation, it will actually allow you to detect particles of a super heavy mass. And so to give you just one example of that, if you can measure electron at a 10 to minus 27 electron centimeter sort of a dipole moment, you will be able to rule in or rule out the so-called SUSY, supersymmetrical particles. Those are the extensions of a standard model theory. The current technologies of quantum sensing can allow us now measuring down to 10 to minus 29 electron centimeters, essentially allow you to rule out the supersymmetrical particles in existence at 10 TeV energy scale. And it's worth thinking about staying here for a second. We all heard LHC, big story of LHC was the discovery of Higgs boson in 2012. After that, have you heard any more stories about LHC? No. And so people have been, high energy physicists have been asking, well, please, let's invest another $40 billion. And we'll take it maybe 30 years to build a factor of 10 larger scale of LHC. And that will allow you to access energy, maybe 10 times more, 100 times more. But if you say, no, it's a desert, from tens of GeV to tens of TeV, there's nothing there. Because you're doing those experiments with quantum science that's telling you, don't look unless you build an accelerator that's actually in the universe, because it will be, you need to build an accelerator that's bigger than the curvature of the Earth. And that will have an impact on big science. Yes? So and that's what I'm saying, tabletop experiments in quantum technology can have big consequences. You talk to experimental physicists in particle physics, they remain to be healthily doubtful about EDM experiments. You talk to any theorists in high energy physics, they take this very, very seriously because time reversal symmetry has to be violated. And if you're not seeing it, that means 10 TeV energy particles are not in existence. It's a close on the emperor. And so these are the things I think I just want to emphasize, how do you do that? It's like a magnetometer I was telling you about. You have two energy level systems. You put an electrical, now it's not sensing magnetic field. I want to sense electrical dipole. I want to put an electrical field on. And all you need to do is to apply electrical field and see that level move around, because that will tell you that D dot E will have energy level shifts. And you have to do these experiments precisely to be able to really place constraints. And so the modern quantum science is now working on molecules, cooling molecules down to extremely low temperatures and put them one by one in optical lattices and so on. You start to use these type of experiments to constrain the existence of electrical dipole moment. And the progress of the past few decades indeed has now advanced from 10 to minus 25 e-centimeter back in the 90s, all the way to mid 10 to minus 30 now. And this is where I was telling you, this is starting to constrain the existence of the mass scale of the supersymmetrical particles at a 10 TeV scale. And I think one can expect this to continue to advance by another factor of 10 and so on. That we will be talking about 100 TeV. Maybe you will discover EDM at that point, that you will actually make a discovery. And that would make an incredible major impact on our understanding of the basic fabric of particle physics. Or you will say, please, up to 100 TeV, don't bother to build an accelerator. Let's not spend $40 billion to do that. Now I want to, yes, please. Yeah, you're saying why not atoms? Is that what you're asking? That's because in the molecules, inside the so-called body fixed frame, the molecules, oftentimes you can hear molecules are polar molecules, meaning inside the frame of its body fixed frame, you have a huge electric field that's already there. And so you can use a little feeble field in the laboratory to orient the molecules. You're using very little electric field in the laboratory to manipulate a huge field inside the molecule, and that's an advantage. So I want to come to tell you another story, which is atomic clock. Actually, that's the remaining of my talk will tell you is about atomic clocks. And that's because atomic clocks, as I'm making the analogy, is our telescope and a microscope. If you, as I mentioned earlier, if you can scale your atomic clock to the level of 10 to minus 20 sort of a measurement precision and so on, you don't have to build microsync interferometers to measure space ripple. Just build a clock and compare two clocks. When the gravitational wave comes, you should be able to tell. There's a, it goes back to when Einstein was cooking up a relativity theory. Remember his Gedanken experiment, he always had two little men on the platform when the train goes by. Every single experiment, whether he in the elevator, when the universality of the fall, or whether it's the relativistic thing, it's always the two little men have clocks. Well, these are the two little men have clocks, or two, that you can actually use this to really test all the fundamental theories of relativity, and beyond. And I will tell you some exciting developments where maybe we can start to see the conflict between relativistic physics, which is always deterministic, and quantum physics, which is not. And maybe we're getting to that level of measurement precision that you'll start to see the conflict between the two. The dark matter I mentioned earlier, imagine you can build these incredible long baseline quantum network and connecting these quantum clocks together, and this will be the most biggest telescope you can imagine building, and you can image the edge of the universe. You can hear the Big Bang echo coming back. A microscope side of things, you can of course use clock as time and space are connected. You can use this to look down at our Earth and see the weather changes, the ocean level rising, continental drifting, and so on. So let me go back to the basics. It's a summer school, and I think maybe we have been buried all these advanced algorithms and so on. It's interesting to look back a little bit. Maybe it's too simple, but I just want to go through that really fast for you. The quantum physics, it's an ironic thing, right? The reason why the advance of technology has gone so fast over the past 6 decades and so, or 100 years is that quantum science gives us two things. One is the certainty, the absolute certainty. The other one is the uncertainty. It's really funny. Quantum physics is what gives us measurement standards that we can all trust. At the same time, the only noise is also comes from quantum physics. There's nothing else because of quantum fluctuations. So I want to just kind of emphasize this yin and yang aspect of quantum science. You know, the certainty that goes back to Bohr's theory, which is not an accurate quantum physics, but it's a reasonable. He was the first one to describe these orbitals as a quantum trajectories of quantum electrons moving around nucleus. The energy levels between the two trajectories are fixed. Okay, and it's a fixed by nature. It's a fixed by whatever you want to believe in. By when the universe is built, maybe you can say from the Big Bang to now, the fundamental constants is not a constant, so the energy level can change. But at least now, in the modern epoch, when you make those measurements, whether you do it in Oak Ridge or do it in Boulder, Colorado, they should give you the same measurements if it's done correctly. On the other hand, we also know the only reason why we have noise is coming from superposition. You have a Hamiltonian, you write down your eigenstates, there is no uncertainty. But when you put your system into a superposition between two eigenstates, and then when you try to make a measurement, you don't know which eigenstate is going to be measured a priori. And so in this case, in kind of a clock application, you can think of, I put a superposition between ground and excited state. There's energy gap E. So if you waited the time T, there will be a phase evolving between the excited state and ground state. This is the factor E to the IET. This is when you are building clocks. That's what you want to measure. However, if you put a system in coherent superposition like that, and you try to say, at this particular moment, I want to measure this atom, whether it's in the ground state, excited state, we know you wouldn't be able to know that a priori. There will be so-called quantum projection noise, because you don't know whether it's going to be turning E or G. And that's really the only reason why we have noise. And here's an example, like we talk about quantum coherence, and I just want to give you an example of the modern technology of how well we can control quantum coherence. So here's a picture of electron moving around nucleus. It's running at a period of 10 to minus 15 seconds that people call it 1 femtosecond. If I slow down by 15 orders of magnitude, it looks like 1 cycle per second, like a quantum pendulum here. Macroscopic time scale of the universe is 10 to the 18 seconds. You take a geometrical mean between the microscopic time scale of 1 femtosecond and the macroscopic time scale of a universe, which is 10 to the 18 second, it's a couple of minutes. And turns out we can now control these quantum coherence, these quantum pendulums, exactly a few minutes kind of a coherence time. Tells you, your coherence time is at the midpoint. You can let this quantum pendulums oscillate for 10 to the 17 times before it decoheres, almost as if somebody built a pendulum clock at the beginning of the Big Bang, and it's still oscillating today. Fractionally speaking, they are the same number. That's what a geometrical mean means. So that's why quantum coherence at this scale allow you to now precisely measure time to such number of digits is because of the quantum coherence is so great. At the same time, you have to build really coherent laser systems to be able to follow these quantum pendulum of electrons moving around the nucleus. And so you have to build highly coherent lasers. Towards the end, I will tell you a quick story, but for the moment, we'll focus on the atom side. And because each atom has this uncertainty, this is so-called a standard quantum limit in quantum sensing, the precision scales was 1 over square root of the number of particles you use, or the number of measurements you make, right? The quantum fluctuation is white noise. And the more measurements you make, the more accuracy or more precision you achieve, but scale is the square root of that measurement because the numbers, this noise are uncorrelated. But what if you can correlate the noise? You have all heard about entanglement. What if instead of these 5 quantum pendulums all have 5 different copies of a random noise that's completely uncorrelated? What if I entangle them such that you only have 1 copy of noise and you still have n copies of a signal? Suddenly the scaling changes from 1 over square root of n to 1 over n. If you think about that for a second, this is where the quantum advantage is. Having quantum particles to be correlated such that noise is no longer random. Only 1 copy is truly random, but the rest of the other particles follow each other. If you think about that, the quantum computer is exactly doing the same thing. This is what all these gates and all these things are about. It's basically different. This is the simplest possible sort of a quantum algorithm. It's just 1 circuit, but a quantum gates is trying to keep that correlation going as you manipulate, add more and more computational complexity into the system. But fundamentally, you are trying to make sure these quantum particles are correlated such that 1 copy already knows the other of the fluctuations. And so indeed, this has been the story of advances of clocks over the past 3 decades of quantum systems, and goes back to that question that the student raised. How do you keep track of these many fragile quantum systems to make sure that you can manipulate them and yet they're not decoherent due to the environment? So first you find quantum systems that has a very high quality factor Q that I mentioned earlier. You want to build with as many quantum particles as possible because that allows you to average it down to the so-called standard quantum limit. But then you want to take advantage of entanglement and so on, such that your scaling can be much faster. And that would be the true quantum advantage. And again, I want to emphasize we have not reached that. We can build these quantum many-body states. We can understand the complexity of quantum magnetism, at least starting to explore this 3-dimensional Ising model. That's actually very difficult to calculate with the classical computers. And you can start to do quantum simulation experiments. So this is Carlton's talk was all about. But can we really realize this quantum systems with entanglement such that it will build a clock that's better than, I have my clock at 10⁻20, and yet in its entanglement, I can get to 10⁻21. No, we don't have that yet. But it's coming. I so strongly believe, I'm a big believer of quantum science and quantum computer science. I just want to make sure we are grounded on each concrete steps that we're making advance. So it's actually interesting. I take not all of you are from AMO physics, and so I want to just give you a little bit of an AMO physics side of the tool of the past several decades of why the science and technology have moved so fast and so much together. For example, the quantum control technology in the 90s allow us now to achieve very high quality factor, the optical transitions that I talked about. Laser technology continued to advance since it's invented. We can now have optical coherence approaching a minute. Okay, this means you can have a laser light in principle from Earth to the moon and running back and forth hundreds of times. And you come back, you still know you are on the peak or trough. You still know the phase coherence. Frequency comb allow you to synthesize electromagnetic fields. Quantum gas allow you to build these quantum many-body states, 1 atom at a time. You heard about tweezer experiments. And this is a so-called optical lattice where you cool atoms down to a very, very low entropy. Molecules are also now included in this category. And you can see that the progress of the clock is going on a different, talking about Moore's law. Yeah, this was microwave clock. It's coming down 1 decade, performance improved over every decade. It's amazing, but it's hitting the wall here at 10⁻16. The optical clock has picked up steam over the past 20 years, and it's still ongoing. We'll see when this is going to hit the wall, but it will have a new technologies already cooking also. And so because of that, you can see the science, technology is moving forward tremendous amount. The precision has reached the mid 10⁻21. The accuracy has reached the 10⁻19, mid 10⁻19, and so on. And that's still ongoing, this revolution. But I want to just go back a little bit to tell you why the past 30 years has been so special. And that's because of science, as we learned how to, for example, laser cool atoms, like the picture that's showing on the animation here. This is a Nobel Prize winning physics in the late 90s, but now it's in every undergraduate teaching labs. These atoms are tremendously hot in room temperature, and yet inside the glass cell, you're sending in laser beams from 3 different orthogonal directions. And you wait a millisecond later, if the light frequency is tuned just right, the atoms always absorb light from an opposing beam against its motion. You can cool them down to microkelvin or hundreds of nanokelvin in just a few tens of milliseconds of time. And because of that technology, you can start to think about macroscopic quantum systems where if you cool them down further, you can form a new form of matter. It's called the Bose-Einstein condensate. And these 3 gentlemen shared the Nobel Prize in 2000, where the macroscopic quantum mechanical wave functions, because of the de Broglie waves of neighboring atoms, start to overlap. And so if these particles are bosons, they all condense to the quantum mechanical ground state. And you can see that where there's no entropy left. And you can then partition them into 1 particle per lattice well. And that's where you can start to think about these optical lattices and so optical tweezers and so on. And this all happened only just about 20-something years ago, right? But now it's a routine technology that we use. If you have heard about neutral atom quantum computer, I know that Carlton just talked about it. It's all coming from this kind of technology. Then around the same time, another pioneer, her name is Debbie Jing. Unfortunately, she passed away. She was the one who created, instead of bosons, creating Bose-Einstein condensate. She was the one who started to use fermions. There's two kinds of particles, bosons and fermions. If they're identical, one has to be symmetrized, the other one has to be anti-symmetrized when you exchange the 2 particle position. And she was the first one that was able to show when you cool down just like a fermions, the bosons show very, very distinct features where every energy level is occupied by 1 and only 1 Fermi particle. That's what we learned about periodic tables and so on. But finally, you can do this in the lab. And she can show you where the Fermi energy is by the, if you had 1,000 particles, by the time you occupied all 1,000 energy levels, that top level is your Fermi energy, just like we learned in condensed matter physics. And so you can immediately see these kind of systems allow you to have a native fermions. You don't have to build quantum gates on bosons to simulate a fermion. Why not just using native fermions to do understandings of the Fermi physics in condensed matter? And that's what the powerfulness of these kind of quantum systems are coming from. For myself, when I was a student just like you at your age, I was building my lab, and I said, oh, since Debbie has given us the Fermi sea of ultra cold atoms, maybe I want to learn from heroes like Dave Wineland. Here's Dave Wineland. You have heard his name. He was the first one who built the gate, quantum gate in trapped ion. Why does Dave want to build a gate? Well, at the time in the 90s, they had this one single trapped ion that was the best atomic clock. But Dave said, well, maybe that's not enough. Maybe I need to build 2 because 1 takes a long time to average it down. If I have 2 or 3, obviously wins. But if I have 2 and 3, if I can entangle them, that will win even more. And that's really where all the story come from. And Dave, of course, shared the Nobel Prize with Serge Haroche back in 2012 for his work on controlling a single quantum particle. But he also is the one, I think, that first demonstrated the quantum gate with Chris Monroe. So as a youngster, as a young graduate student or young professor, you can think of, what if we can build many, right? Instead of just 1 or 2, what if you can put it, since we already have a quantum gas of atoms, why don't we put many of them together and you can have a long quantum coherence? Maybe that's the way, if you want to really advance the clock precision, that's the way to do it. Put lots of particles, and the goal is to solve the problem of interactions and to make sure every particle goes back to the same question, the challenge of making sure you put 1 million particles in there and every one of them, the quantum coherence is being protected. And later on, you can even put quantum gates on those to allow you to build even better precision using quantum entanglement. There's one more issue that we had to solve at the time. That's because trapped ions are charged, so it's easier to be trapped. Neutral atoms, you cannot just put electrodes around them. You actually have to polarize it. And And the way to polarize it using another Nobel Prize winning technology, this is Arthur Ashkin in Bell Labs in the 70s. He invented a technique called optical tweezer. The idea being you focus the laser beam down, you can polarize any object, including atoms. When it's polarized, you are creating a spatially dependent potential energy difference at the laser focus versus outside of the laser focus. You can attract the atom, like a tractor beam. And this is the same technology we are using. We trap atoms using this optical tweezer. You know, you heard about this. It's coming from Ashkin's technology. If I want to build a clock, or for that matter, if you want to build a quantum computer, and this is your qubit, ground state, excited state, you want to make sure every atom is treated the same way, and you want to keep the maximum coherence. Well, one thing you need to do is an ordinary optical trap. If you just put any laser beams on, very likely the ground state and the excited state will have a different trapping potentials. One could be even anti-trapping. So you have to find another wavelength such that both the ground state and excited state shares the same trapping potential. And this sounds extremely simple once you cook out that idea. But it's a fundamentally important idea in the sense that because you can make the two trapping potential exactly equal, you can actually separate, just like in the trapped ions, you can finally separate the motional degrees of freedom as the particles that's rolling around in this harmonic potential versus the internal degrees of freedom, which is the spin, ground state or excited state or your qubit. In the sense of when the qubit is flipping, it wouldn't matter whether it's on the bottom of the trapping potential or the top of the trapping potential because the two wells look exactly the same. Okay, and this was really the ideas that worked out. Jeff Kimball was my actually postdoc advisor when I was at Caltech. John Presco used to come to our lunch tables in the late 90s. We were used to talk and learn the quantum information science from John Presco, just like you guys are doing. And Katori, who's a professor in University of Tokyo. And that allowed us to trap many atoms. And then when you drive the transition of the spin qubit, this is, if I use the language of a qubit, this is your qubit, ground state, excited state, except this qubit is separated by optical frequency. Okay, it's not a microwave qubit, it's an optical frequency. You use lasers to drive it. But as you drive this qubit, you can see the motional degrees of freedom. As we all know, optical qubits are difficult to manipulate because optical wavelengths is so short. Whenever you are flipping quantum states, it's very easy to have a Doppler effect, a so-called motional effect. But because of the trapping like this, you're controlling these atoms in the ground state, motional ground state. These so-called motional Doppler effect are now removed from the center, the drive as you flip the qubit, as you look at the clock transitions. This transition, so-called carrier transition, carries no information of the Doppler shifts. All the Doppler motional effects are manifested in these two sidebands. One is called a blue sideband, the other one's called the red sideband. The reason why the red sideband is suppressed, and in fact that we can actually completely suppress it, is because you already cooled the atom to the motional ground state, and there's no more states below the motional ground state, therefore you cannot drive it. The red sideband should be completely zero. The fact it's not completely zero will tell you the temperature is still a little hot, not in the quantum mechanical ground state. So you can use this to start to build atomic clock. You can have hundreds or thousands of these 2D layers. This can be formed by having a laser beam retro-reflected by a mirror, forms a standing wave. And the standing wave has anti-nodes that can trap these atoms polarize them and trap them there. And your clock laser can come in and do a spin rotation. This is your qubit spin rotation that I was explaining, except that these atoms can actually interact, even though these are fermions. The fermions need to be anti-symmetrized with respect to their wave functions. And you can see the internal state spin degrees of freedom is symmetrized. The motional degrees of freedom is anti-symmetrized. So they can still interact, except very feebly, so-called P-wave interactions. And you can find ways to solve that interaction problem. But it actually turns into clock into a many-body spin interaction, just like the Ising models that Carlton was talking about. And this gives some new insights for example, in the most recent rendition of our clocks, we actually build extremely shallow optical lattice, where you can think of these are different 2D pancakes lined up against gravity. And if we turn up high school physics knowledge, we know that atoms are trapped on each individual layers, but between layers, there's a so-called gravitational potential energy difference. This is not Einstein's relativity. This is the high school physics of a potential energy difference. And you can see the ladder is tilted because each level, each trapping side has a difference of a potential energy mgh. H happens to be the height, and the height is λ/2 in this case. But because we are using the trapping potential for the ground state excited state to be exactly the same, if you think about you are driving this transition from the ground state to the excited state, the excited state will experience exactly the same trapping potential, looks like that. And because the trapping is so shallow, the atoms is no longer confined in individual pancakes here. The quantum mechanical wave function actually spreads out. When you go to very shallow lattice, if you have taken some very basic condensed matter solid state physics, you will know the so-called block band. The atom wave function tends to want to tunnel, and they get spread out. So it's kind of interesting. You can see the wave function, it's shadowed, calculated so-called Wannier-Stark states. Looks like the wave function is spreading over several sites, which means that the atoms in single site can interact with so-called P wave because they are identical fermions. But from neighboring sites, they can actually interact with the S wave because they are non-identical fermions. And you can use these interactions to cancel each other so that interaction effects can go away. This is the tuning the Hamiltonian. This is exactly what, in some sense, you look at the quantum simulation experiments Carlton was talking about. Remember, there's a knob he wants to turn. This is the knob we are turning in the Hamiltonian, how the interactions can be tuned, fine-tuned by lab parameters. And you can do very precise spectroscopy by driving the atom on the same site. You can also driving atoms into a weird superposition where the ground state is sitting in one location, but when you drive to the spin up in the excited state, it sits somewhere else. So imagine we are all sitting in this room, we are listening to this lecture. There's another a laser come down, excite all of us. We become a quantum particle. Some of you are still here, but some of the other half of you is actually living upstairs. And it happens to be upside down because you're spin up, spin down. I just trying to make some animation. I know sometimes it's always very cheesy to using classical physics to explain quantum, but yes. The cancel meaning the suppose S wave interactions gives rise to positive frequency shift. P wave can be tuned to have a negative frequency shift, and you tune the strength until they are exactly matched. So that then the clock has no more frequency shift due to these interactions. The reason why I'm making this comment about this superposition is that we are actually doing this experiment right now. You can prepare atoms in coherent superposition up and down, and then you'll move them apart. One live in the basement, the other one live on the top of the floor. And you can let them dangle there for a couple minutes, and you start to measure what's the gravity, what's the time constant, what is the gravitational relativity effects. So it's actually quite exciting. Imagine you have a set of atoms. We actually can take an image of those. These are CCD camera image of the atom distribution along gravity. And you can think of as two sets of a pendulum that's oscillating on the upstairs and downstairs. You prepare them in coherent superposition, so they're oscillating in phase. You wait for 6 seconds. You can see it used to be oscillating in phase would be just a single line up and down. But you start to see a little angle opening up, a little ellipse opening up. If you wait longer and longer, it opens up more and more, indicating this set of pendulum has a slight time difference. Now this time, it's not because of the gravitational potential energy. I've taken care of that. But there is a fundamental difference in time. The atom that's living 100 micron below the other atom, you can see the phase difference they're picking up. And that phase difference, and we can actually measure this for like up to 2 minutes kind of a coherence time. That phase difference comes from Einstein's general relativity. Remember, we live on Earth and our space-time is curved because of Earth's gravitational potential. That means the clocks closer to the Earth will run a little slower than clocks that, you know that, you use GPS every single day. That's how we founded the lab here, right? When you drive down. But it's actually fascinating to think now you can actually measure time difference over just a human hair width. You move your clock up and down by the width of the human hair, you will see time is running differently. And that makes you wonder, what if you keep going? What if you get to the point where your sensitivity, your precision of your clock is so good over one de Broglie wavelength, you can see because the Broglie wave is distributed across gravity, you can actually see the time is running differently. Suddenly, when I say there's a coherent superposition between excited state and ground state that's sitting there spaced apart by, say, 100 micron, you wait for a while, you'll find they will be decoherent due to space-time curvature. And this is the time I was telling you, for the first time, we can start to dream about the quantum uncertainty, because the superposition have uncertainty built in, versus absolute certainty. When Einstein write relativity theories, it's always borderline. When you have a borderline, you start where your C and T is, you know where you will be later on. But now we can start to think about maybe a conflict will come and we'll be able to see many body dynamics that's directly influenced by the gravity in the next 5-10 years, I think. To do such experiments will be difficult. We needed to continue to advance the clock precision further. And one trick to do is the entanglement. This is what we have always been talking about. What if we have quantum advantage? Well, there obviously you can look at the picture like this. There will be a tremendous advantage if you can all squeeze the noise away such that you have just a very small sliver of a little uncertainty and that's running around the equatorial plane, and that will allow you to measure time much more precisely if you can make all the noise of n particles to be correlated. And this is what I guess 2 years ago, the Nobel Prizes for the Bell pair, talking about the first entanglement demonstration between photons. But you can do the same thing with atoms. And if you can do that by, for example, using cavity QED technique, where you can, here's our clock, and we can make this optical lattice act as if it's an elevator. We can actually load atoms down here and just move the elevator up. And we can literally do that. We can just move atoms up and down and put a sample of atoms in between the two highly reflective mirrors. So these thousands of these atoms look to the left, look to the right. They look identical, and they look they're looking through each other's image thousands of times, and they get spin entangled. If you find that magical, I can explain that to you later. But this is how you can actually use these techniques of collective measurements of a single photon. Wouldn't be able to tell which atoms interacting with it. And the consequence of that is these thousands of atoms become entangled. And so you can move sample A and sample B, sample A out, put a sample B inside, and you can do multiple entangled states, and you can make a comparison. And indeed, we are starting to show by doing spin squeezing, you can do better than the so-called standard quantum limit. This, however, you can see the unit here is 10 to minus 17, 10 to minus, and it's nowhere close to be 10 to minus 20 numbers that I was telling you about. And this is what I was trying to tell you. This represents the best clock measurements with entanglement, but it's 3 orders of magnitude away from the best clock measurements without using entanglement. Plenty of quantum science in there with optical lattice and so on, but no spin entanglement yet. But on the other hand, this is rapidly improving. So I do think the advantage of quantum science using entanglement. I think we should be careful when we say quantum advantage. I think we enjoy quantum advantage every single day. It's just a very specific quantum advantage of entanglement advantage is not, it's still elusive, but it will come. And I want to end my talk by thanking people in Oak Ridge here. And I want to give you a talk. I hope you'll find it very, very exciting, because this is a new physics that's just happening today, that we can now think about building these atomic clocks and so on. Well, is it possible one day we can build a nuclear clock? Yes. Atomic clock is about measuring time of electrons moving around nucleus. What if the laser light can go in and directly changing the state of a nuclei? Would that be nice to be able to build a nuclear clock? So to talk about this, I want to show you two more very recent advances in science, in technology, lasers, for example. Here's the electromagnetic spectrum. We can build the lasers extremely precisely now. If you zoom into the visible spectrum and you zoom down by a factor of 1,000,000, you have lasers that we use in the lab every day, the diode lasers that you have seen for some of the experimental physics students. We can stabilize it using technology that invented by Jan Hall and other pioneers. This is the technology, by the way, is used for detecting gravitational waves, stabilizing laser wavelength or laser frequency onto a Fevri-Perot cavity. And now the modern technology, we were able to build a much better Fevri-Perot cavities using crystals and so on, like silicon crystal in our lab. And that allow you to achieve very, very good coherence time, or another way of saying the laser line width becomes extremely narrow. We're talking about 10 millihertz or so of a laser line width. And that's the optical oscillator that's oscillating at a 10 to the 17 kind of a quality factors here. And there's around the turn of the century, there was a new technology came along and exceedingly simple to explain. It's nothing but a Fourier transform. If you have a train of pulses, if you Fourier transform it, it's a repetitive pattern of frequency markers in the frequency domain, right? This is something we all learned, again, maybe in the first year in college or something, Fourier transform. I don't know when you learned it. But this is something we ingrained in our mind. And you will laugh at it if you say, well, somebody won the Nobel Prize because of this, which is literally true, except that it's very simple to think of this. It actually takes another matter of being able to generate this spectrum like this, like a beautiful rainbow, and being able to digitizing every single color in it with a frequency marker. And that's called the frequency comb technology that allow you to build now a laser that's stable in one location. And it's through this phase coherent gear, you can basically distribute the color to any location you want it. That's the Nobel Prize of 2005. Jan Hall happened to be my thesis advisor, so that's why I knew. Okay, so with that, you can use this kind of frequency comb. We can actually now compare clocks. I've been talking to you about clocks in our lab. We have a neighboring lab, which actually the NIST, National Institute of Standards Technology, they have optical clocks. We can connect them through the fiber network or even through air by sending these optical frequency combs. We can compare clocks of very different kinds of atoms. So this is really important to be able to take clocks out of the laboratory for real use. But and here shows the comparison between clocks. But now I want to come back to the question, because I want to pay tribute to the people here. This is because we got some nuclear material from Oak Ridge. And this is the thorium-229, and only Oak Ridge has the stockpile of thorium-229. So imagine that you say, I want to do exactly this atomic physics except with nuclei. I want to have a laser to be able to drive the nuclear transition. And you obviously need to build a coherent laser at a VOV, vacuum ultraviolet, or maybe in the future in the X-rays, just doing this kind of the same physics that we have been doing in atomic physics. And we were building frequency counter as the frequency comb, and you need a special nuclei. And that's what I think the Oak Ridge is so important. This thorium-229 happens to be the only nuclei that has low-hanging energy levels around 10 eV. It's actually 8-point-something eV right here, that right in the thick of atomic physics that we do. And I will be able to generate coherent lasers at this wavelength to drive this nuclear transition. The next one is the uranium. That's a 14 nanometer. That's going to wait another decade or so, hopefully. But it turns out it's really interesting. I just mentioned about frequency comb in the visible. There was another Nobel Prize last year, if some of you heard, called attosecond physics. What attosecond physics was about is if the electric field of the laser beam is so strong, you can distort the Coulomb potential such that electrons can move out of the, being confined by the Coulomb potential of the nuclei And when the next cycle, they get snapped back. And during this violent recombination process, you can generate so-called high harmonics. That's what people are doing attosecond physics with it. These are the three people that won Nobel Prize last year on attosecond physics. So the question you ask yourself, can you combine these two techniques? We have conquered frequency comb in the visible. Can you use the high harmonic generation process to conquer VUV, vacuum ultraviolet, extreme ultraviolet, X-ray regimes? And the answer turns out to be yes. We can actually use, what we needed is to be able to generate very high repetition frequency, meaning pulse coming over very short periods of time, but having very strong peak power, peak intensity, to be able to essentially ionize these electrons and then let them recombine to generate high harmonics. If you can do that, then you can combine these two things and essentially translating the frequency comb from the visible all the way out to the deep UV and extreme ultraviolet.
I just wanted to say you've got 10 minutes left.
Yeah, I need 2 more minutes to finish. Thank you very much.
Great.
And you can, for example, we actually do that by building these frequency combs inside the fibropleural cavity. That every comb tooth that I showed you here is being enhanced by a corresponding cavity resonance, and you can combine these two physics together, two technologies. And this is actually the first time we applied on May 12th. The student at midnight saw this nuclear transition. It was super, super exciting. Like 12 hours later, the news was all over the American Physical Society. He got an invitation in 12 hours, like from the first data set of being able to see these nuclear transitions to where the results being written up. And for the first time, we can now frequency connect the strontium atomic clock with a nuclear clock with 12 digits of precision. And this is the first trial. Also, this paper was super fast reviewed, immediately accepted. But what's really exciting, I want to connect to the nuclear physics. I know that's what I feel like. It's the fundamental physics side of quantum science is just amazing revolutions happening right now. You look at the nuclear physics, and in Oak Ridge, of course, it's the epicenter of nuclear physics. But now you can see there's 5 transitions here. I can directly measure them without any electrons. This is directly driving the so-called nuclear quadrupole interactions at 148 nanometer. These are the absolute frequencies. And because I can measure these nuclear quadrupole moments directly by driving these nuclear transitions, I can actually measure, for example, what is the quadrupole moment ratio between the nuclear excited state and the ground state with a pretty amazing precision. And turns out this measurement will ask for the volume of a nucleus to be different between the ground state and the excited state by 0.06%. So you can see the precision of AMO physics start to come onto the nuclear physics, telling you actually the volume. If you say, well, the nuclear state, the volume is constant when you go to the ground state, excited state, it's actually not true. And you can test this with the 4 digits. So I think this is a perfect place to end. I want to connect all the way back where the nuclear physics started for material science, like Mossbauer spectroscopy. All of you have heard about this, right? It's kind of amazing when you have a nuclear decay and it gets absorbed in a material where the recoil of gamma rays is absorbed by the entire material. And this was actually the first experiment people tested, this so-called red shift. The term was coined when Pound, Rebgar, they did this famous experiment in Harvard, where they have a nuclear material at the basement, and they put an absorber at the top of their building, and you can see the photon frequency was redshifted. And yet I showed you the experiment where we can measure the clock being different by just 100 micron or so. And there's a connection between atomic physics and nuclear physics right there. But now with nuclear clock, this connection is no longer superficial. This connection is really deep. So with that, I want to, I think I end here. Thank you very much.
Go ahead. We have time for questions.
Yes. Yeah, no, that's an excellent question. Uh, it, one of the most important answer to that is, wouldn't it be great to compare QED against QCD? Nuclear physics. Yes, you can say, well, what's the usefulness about keep pushing the precision higher and higher? One is that the precision needs to be higher. That's because you need that kind of a high precision to test. Wouldn't it be amazing to measure quantum gravity directly with a clock? Unfortunately, our precision we're talking about right now is not close, not even close. But if the fundamental constants is not a constant, you can compare a lot of atomic clocks against each other. You seem to be doubtful about that statement, which I am as well. But we know we cannot be doubtful about, we have to be open-minded, because where do we come from? A Big Bang. This is singularity. Well, something must be different in the beginning of the physics because we don't have a model for it. Who tells you that the fundamental constant alpha has been constant since the beginning of the Big Bang? Probably not. And you will say, you probably will never be able to find out because the universe has settled. Well, maybe that's not. Maybe you can look at the spectroscopy lines from different galaxies and comparing what's observed on Earth. What I'm trying to say is, if you were able to say nuclear physics, a clock measurement to the level of precision with atomic physics is all QED physics, right? Electron versus photons. Nuclear physics, there's a strong force inside. And if you start to compare them and you see things start to drift, that makes you wonder what's going on. And that's one area of fundamental physics. Well, people say fine structure constant is actually not a constant. But how do you test those? Well, that nuclear clock will give you this one knob. The second is really more on the, I would always say the human curiosity. Quantum gravity is far, far fetched at the moment. Unless we get to the near the black hole, we really wouldn't be able to test those. What I told you about the conflict between certainty and uncertainty has nothing to do with quantizing the gravitational field, because Earth's gravitational field is too weak to quantize. It's all linear in the sense. But on the other hand, if you keep pushing on it, you will start to see very interesting, where the quantum decoherence is coming from, and so on. Maybe if nothing else, if you are only interested in building quantum computers, well, maybe eventually will tell you should build your quantum computer as a flat, thin screen instead of vertical, because it will be all decoherent because of gravity. I'm making a joke here, but no, these are the things that you really come from making precision measurements so good that you will have discoveries. You don't know what you're going to see. That's the other aspect. When you build a microscope, a telescope, when Galileo first pointed his telescope to Jupiter, he didn't know he was going to see like 7 rings, those rings and the satellites, right? And so that spirit of being able to explore should never be lost. I think sometimes you hear, especially currently, quantum computer, oh, it's all engineering problem. All you need to do is to just build the qubits, wire them up, and it's there. That's actually not true. Completely not true. I don't buy that at all. There's a real fundamental challenges of how many qubits can you wire up? Is the error correction really going to be able to scale the way such that you will show true quantum advantage when instead of you have just abundance of a resource that's continue to explore? So these are the questions. I think in some sense, you're just pushing the frontier. But there are some real strong motivations of, if we can make VUV, XUV coherent light under control, what if one day we can get it to 14 nanometers or 1 nanometers? Then suddenly it's not just thorium. You can have bring these nuclei. There's all this kind of physics up here will totally change. You have a renaissance, just like when laser was invented, atomic physics had never been the same since laser was invented. Imagine you can use lasers that excite the nuclei and so on. That would change the nuclear physics. Yes, the question back and then in front. The question is about the quantum coherence and decoherence. Is that what you're asking? Yeah, the quantum gravity, I want to make sure that I want to clarify, I'm not touching quantum gravity. The quantum gravity truly requires a very strong gravity field that you want to be able to quantize the gravitational field. And so we are not talking about gravitons here. And however, imagine, so I tell you one example. If you have I was telling you, I can put atoms in coherent superposition here and there. And if the atoms here and there are moving at the same speed, then it doesn't really matter whether you're whether you're superposition between the horizontal plane or on two different vertical plane, doesn't matter. But if the vertical plane actually has a different time that's evolving, then after you wait a little while, there's a phase difference that's been developing. And if you have multiple planes, there's a phase difference will all be different, and you'll start to lead to decoherence, especially if you have multiple particles. In some sense, the gravity, the space information gets wrapped into the time. And so this is the one area that's both in terms of understanding physics, like many body, especially when you have a many body physics. If you have only two particle physics, you can say that's just a simple phase shift. That's something simple, it's dephasing, or something you can just capture the phase shift. But if you have many particles, you actually can have a real genuine decoherence coming in. But if you understand it, of course, you can look at how you avoid that problem or how you use that problem to your advantage. Yeah. So I think, of course, this kind of physics is happening right now. It's just that we don't have a way to be able to see it. It's like we don't have the right microscope to see those physics. The physics is always there. But what we are building is building these quantum systems allow us to actually see those effects in a very microscopic way.
Well, I would love to thank June for
Time's
his
up.
wonderful presentation. And if you have further questions, are you around for lunch? Then
Yeah, absolutely.
yes,
Yeah, no,
wonderful.
Next 3 hours.
Yeah. Continue to find him and you can keep asking questions. So thank him again.